The last section on gases is stoichiometry. Yeah, we'll never get rid of stoichiometry. It's the most important thing in chemistry. Anyway, so we'll do stoichiometry and then we'll talk just a little bit about speeds of gases and just even tad bit little, even smaller than that, like nanobit about real gases. All right, so gas stoichiometry has to do with, reactions where you have gases. So we have done solid stoichiometry, we've done solution stoichiometry. In gases, we're going to have to deal with, of course, you got this, the ideal gas law. Okay, we have to work with the ideal gas law in order to figure out the moles of gas or the volume of gas or the pressure of gas that is formed, all of that. So anyway, key thing also, in there, gas stoichiometry. So let's see what we have. So definitely problems. Of course, what else do we have, right, for chemistry? So here we go. When a 2-liter bottle of concentrated HCl was spilled, 1.2 kilograms of calcium carbonate was required to neutralize the spill. What volume of carbon dioxide was released by the neutralization at 735 millimeters of mercury and 20 degrees Celsius? Okay, so let's see how you're going to solve this problem. Okay, so first of all, for any stoichiometric problem, you need an equation. Okay, you need to have an equation, you need to balance that equation. So we have calcium carbonate and we have HCl. Okay, so those are our starting materials. Now, do I expect you to write the whole equation? Yes, in some cases I do. Okay, and I've given you this equation before also. So I can expect you to write this equation also because it's neutralization equation. So neutralization means that you will form salt and water, okay, with this. So in some cases, I will give you the gas equation, okay, because sometimes it's hard for you to figure out what the gas would be. But in some cases, I expect you to write the equation also. Anyhow, so here is our equation and here it is all balanced out and we know the ratio of calcium carbonate to the HCl is 1:2. Okay, we calculate the molar mass of calcium carbonate because we know we are using the mass of calcium carbonate, so we're going to have to calculate the moles, okay, of calcium carbonate. We'll start this problem in a very normal way because we are given the kilograms of calcium carbonate. We need to convert the calcium carbonate kilograms to moles. Okay, that's our first step to do over here. And so we take the grams of calcium carbonate, so convert the kilograms to grams by just multiplying it by 1000. So that's what I do, 1.2 times 10 to the power 3. You know me, 10 to the power 3, 10 to the negative 3. Those are the ones I use for conversions. So that's what it is here, and then convert it into moles. Okay, and then what are we doing here? Since we are working with carbon dioxide, because the question is actually about the volume of carbon dioxide, the mole ratio of carbon dioxide to calcium carbonate is 1:1. Okay, so we need to do the problem up to here so we can see that we have the moles of carbon dioxide. The balanced equation will give you the mole ratio. Without that, you don't have the mole ratio. Okay, if you don't have the mole ratio, you don't have the correct moles. Okay, why did we start over here? We started over here because we were given the kilograms of calcium carbonate. Now, if you want to do this, and okay, I didn't do it over here, but if you wanted to do it, you can write the 1.2 kilogram right here and say, okay, how many liters am I forming, okay, of this? So just like I'm used to writing, with the numbers underneath the equation. So once you have that, now you're going from kilograms to liters. So in order to do that, everything goes through moles, okay? So kilograms to grams to moles and then to liters. That is kind of our strategy, right? So this is not even an issue because this is just a unit conversion. This is normal stoichiometry, and then this one here we're going to have to use the gas law because there is no direct way for us to go from moles 2 liters. Okay, so that's kind of what we're doing. What we have done so far is just we found moles. Okay, now we're going to have to use the gas law in order to figure out the volume of the gas. Now we need all our numbers to make sure that they're also in the correct units. So the moles are given to us now because we calculated that. So 11.99. Pressure was 735 millimeters Hg. Convert that into atmosphere. So remember 760 mmHg is equal to 1 atmosphere. Okay, so divide that by 760. 735 divided by 760. And then convert the temperature, of course, into Kelvin. I don't know why we never give you in Kelvin. We don't do. So, you just have to keep doing this calculation. Once you have all the numbers, then you just have to find the volume. Okay, so just plug in all the numbers and you get the volume. Very honestly speaking, there are only two kinds of gas stoichiometry that you do. One is this one, okay, where you are given the mass of a substance and you have to calculate volume. The other one is going to be where you're given the volume and you have to calculate mass. Okay, so it's just one way or the other. So this one is this one way of going from mass to volume. Okay, so looking at this one, we have calculate the mass of potassium chlorate decomposed when 325 milliliters of oxygen is produced at 22 degrees Celsius and a pressure of 733 torr. Calculate the number of moles of oxygen and then the mass of potassium chlorate decomposed, okay, in here. The balanced equation is given to us, lucky us, okay, this time. Now, if you want, you can go ahead and write the numbers so you have that with you. Again, I didn't write it over here, but you can. Okay, so 325 is the volume of oxygen, and what is being asked is the mass of KClO3. So now we're going from volume to gas. In order to go, sorry, to volume to grams. In order to go from volume to grams, you need to go from volume to ideal gas law, and from there you're going to calculate moles, and then you're going to calculate the grams. Okay, so our strategy is just the opposite of what we did in the previous problem. Okay, that's how it's going to go. Okay, so let's look at this. So the first thing, of course, is, as I said, you're going to use the ideal gas law to find the moles of oxygen, because this is the volume that's given to you. So you have no other place to start with, okay, except for the volume of oxygen. Then make sure all your units are correct. So 733 torr, convert that to atmosphere by dividing 733 by 760. Getting the atmosphere, you have milliliters, convert that to liters, and convert temperature into Kelvin. Okay, find out the number of oxygen moles. So this is, of course, N is equal to PV over RT. And so then you find out the moles of oxygen. Again, I don't know if I need to go over any of this, but you should be fine, right? Calculating the moles. Once you have the moles using the ideal gas law, now all we need to do is convert the moles to grams, but don't forget, you need the mole ratio. Okay, so don't forget the mole ratio, because this is the stoichiometric part, okay, of gas stoichiometry or any stoichiometry. This is the key part, the mole ratio. So you're starting with the moles of oxygen, and then you find the moles of KClO3, potassium chlorate, from the balanced equation. So 2 moles and then 3 moles of oxygen. And then the mass, the molar mass of potassium chlorate, you have to calculate that, and then you get your final answer, okay, for 1.06 grams of potassium chlorate. So you can see either you go from volume to grams or you go from grams to volume. So really, all you need to do is you need to know, am I starting with the ideal gas law or I'm going to finish with the ideal gas law? When you start with grams, you have to do stoichiometry first. When you start with volume, you have to do the ideal gas law first, okay? But you have to do these two things. Let's look at this problem. This is a little bit of a different problem dealing with volumes. Okay, so how many liters of carbon dioxide can be produced in the reaction of so many liters of carbon monoxide and oxygen if all gases are measured at the same temperature and pressure? So first equation, okay, so how many liters of carbon dioxide can be produced? So carbon dioxide is our product, carbon monoxide and oxygen are our reactants. Okay, so you write the equation first and make sure it is balanced out. And yeah, I think you can write this equation on your own also. So anyhow, we have the balanced equation. Now, what is the question? How many liters of carbon dioxide can be produced? So which means that you're asked about how much is this produced? And again, you're given the volumes of both carbon monoxide and oxygen. So this brings us to the fact that we're dealing with a limiting reagent problem. Remember, when you have two reactants, and both of them are given to you, then it is a limiting reagent problem. Okay, so now what do we need to do? Now we need to figure out whether we need to use the ideal gas law or what do we do, okay, with this. So here is the ideal gas law. PV is equal to nRT, okay, and since we are dealing with the amount of gas that we are going to form, right, carbon dioxide, that's the question. So how much carbon dioxide we are going to form? Some of the numbers here are constant. So what I would like to do is I want to show you that here temperature and pressure is constant. R is definitely a constant. Okay, so which means what? The number of moles is equal to the volume of gas. So what I'm trying to figure out is, do I need the moles over here or not? And it turns out I don't need the moles, okay, because I can deal with the volume of gas easily. So I'm trying to cut down on my calculation, okay? Why can I do this? I can do this only because there are some numbers that are constant, that are not changing, okay? And usually this happens when you're working in a reaction system. You cannot have two different temperatures in the same reaction system, okay? So in one reaction system, some of your numbers are going to be constant, okay? So which means that the number of moles is also equal to the volume of gas, okay, as according to our equation. So which means all we need to do, as we do in the limiting reagent problem, is we figure out the lesser of the moles, right? But here we just figured out that moles is also equal to the volume, so we can just use the volumes, okay, over here. Now, here you can see that I'm using liters instead of moles in the mole ratio part. And that's because the number of moles is equal to volume of the gas. All right. So I just want to show you here that again, if you have constant numbers, if you have constant conditions, you can make your life easier, okay, and not more difficult. If you feel like, okay, I need to write moles here, you can write moles. You may not be able to cross this out, okay, but otherwise you can write moles also if it makes you feel better. But that's why I wrote this, that number of moles is equal to the volume of gas, because that is what I'm getting in this equation, okay? So whether I deal with moles or I deal with volume, it's the same thing, okay, at this point. Why? Because pressure and temperature are constant. Okay, so I have 5.24 liters of carbon monoxide, and the mole ratio of carbon dioxide to monoxide is to 2:2, which means same number. And then I have 2.65 liters of oxygen, and carbon dioxide to oxygen is 2:1. So I do the mole ratio and then I get 5.3. So 5.24 is the smaller liters, so that is my limiting reagent. Carbon monoxide is my limiting reagent. So which means that I will be making only 5.24 liters of carbon dioxide, okay? So when you're working with just gases, then your life is a little bit easier. When you're working with solids and gases, then you have to do the stoichiometry in a different way. But when you're just working with gases, which actually a lot of industries do, just have reactants as gases and products as gases, then it's a lot easier to work with gases at that point, okay? Because your calculations become a lot easier. All right, so let's look at another gas stoichiometric problem. A 100 gram sample of aqueous hydrogen peroxide solution decomposes over time, producing liters of oxygen at this much temperature and pressure. What was the mass percent of hydrogen peroxide in the solution? Okay, so since this is going to be a gas problem, I have pressure and temperature given to me. So I went ahead and did all my calculations first, okay, for unit conversions. So millimeters Hg divided by 760 to give me atmosphere, and then Kelvin, and then I have the liters of oxygen. So these are my numbers. And then equation here just to see what I have and what I need. So I have 3.31 liters of oxygen and I need mass percent. So what is my strategy? My strategy is to find the moles of oxygen, to find then moles of hydrogen peroxide, to find the grams of hydrogen peroxide. The moles of oxygen, how do I find that? I will have to find that using gas law. Okay, there's no other way because this is in liters. If this was in grams, I can use mass, right? But this is in liters. So because of that, I have to use the ideal gas law. So here is my formula. N is equal to PV over RT. I have all my numbers already set here. So all I have to do is plug them all in and I get the moles of oxygen. Once I have the moles of oxygen, now I need to figure out the moles of hydrogen peroxide from the equation and then do the stoichiometric part here. Okay, and the stoichiometry is then using moles of oxygen, the mole ratio of hydrogen peroxide to oxygen from the balanced equation, and then of course this is the molar mass of hydrogen peroxide to give me the grams of hydrogen peroxide. What does this mean? It means that in the solution there was 8.78 grams of hydrogen peroxide. That is what gave me the 3.31 liters of oxygen. Okay, but I have another question to answer, which is what is the mass percent of hydrogen peroxide? So 8.78 over 100 times 100, so it literally is the same number, right? Percent of hydrogen peroxide. So this is pretty good solution of hydrogen peroxide. So you can see hopefully by now you're comfortable that if you're given the volume, you do the gas law first. If you're given the mass, you do the stoichiometry first. Okay, so it's just about those two kind of calculations. And if you had everything in volumes, then life is really good. Okay, so that is about gas stoichiometry. And now let's deal with speeds of gases. Okay, gases have speeds. Of course, gases have speeds. They all travel. Like you can smell, chocolate chip cookies or pizza or fries. Oh my God, you can smell fries from far away, right? So you can smell food. So it means that gas is traveling over a distance. So these two graphs here just to show you two different things, okay? And if you don't remember this, okay, I think you will instinctively because they are just so normal that you'll probably feel like, are you really teaching me this? I am teaching you this though. Okay, all right. So when the temperature is high, the gas molecules will travel more. Okay, their speed is a lot more. This was also part of the kinetic molecular theory. Okay, that the kinetic energy of molecules is directly proportional to the temperature. Okay, so the gas molecules will move much faster if something is hotter. And that's why French fries you can smell when they're hotter, but if they're cold, you don't smell the French fries because the gas molecules are all settled down now. So the higher the temperature, the faster the speed of gas. Okay. The effect of molar mass is also very intuitive because the lighter the gas, the faster it will travel. So chlorine is a pretty heavy gas with a 70 mass, 70 gram or 71 grams per mole. Then nitrogen, which is 28, and helium is just 4 grams per mole. So helium travels the fastest and chlorine is the slowest gas to travel. So I mean, both of these things are pretty intuitive, but it's kind of nice to kind of just affirm, that this is what is happening. Then there are other two terms that I would like you to know. If you don't remember this, again, it's not going to really affect your whole life as much, but it's kind of nice to know these terms and what they mean. Okay, so diffusion and effusion. Diffusion is how, actually both of these are about mixing gases. How are they mixing? How is a gas spreading? And this is a really, practically, this is a very important thing, okay? So diffusion is when there is just a mixture of gases. So like you can see these two particles right over here, and they're just kind of mixing together with no barrier, no particular space. So like there is an exchange of gases between the ocean and the atmosphere, right? It's just happening. There is no particular one location where that exchange is happening. It's happening all over, okay, the place. That is called diffusion. Effusion is when it would be happening, the mixture or the transport of gas will be happening from one particular location. Okay, so if you have a balloon, for example, and if you prick that balloon somewhere with a needle, well, that's the only place where the gas is going to go from. Now, effusions are a little bit easier to control if you don't want the spread of gas, because all you need to do is put a tape over it or block that hole, and that will take care of the effusion. Diffusions are a little bit harder to control. Okay, so this is really all about how gases can exchange, or they can mix and move from one place to another. Okay, that's all this is about. Then just a little bit about real gases. Okay, so ideal gases, as I said to you before, was that ideal gases behave in a very standard manner. Okay, and generally most gases will behave that way. But why do ideal gases behave that way? Is because we assume certain things, and also we assume certain conditions. Okay, so for example, the conditions we have is the STP, right? Standard temperature pressure. Pressure is 1 atmosphere, temperature is 273 K, all of that. We are assuming a lot of that. So once you assume that, you will have ideal behavior. And that assumption is also quite okay, because majority of the gases behave like that. But real gases are not ideal gases, which means that they will behave a little bit differently. Why don't they behave in the same way as ideal? Because you've changed some of the conditions. Okay, and the some conditions that really matter, okay, for gases is volume and pressure. Temperature also, but temperature will control these two as well. Okay, so volume and pressure become the big thing. So if you increase the pressure on any gas, it's going to start behaving differently. Just think about yourself also. Okay, if we increase pressure on you during exam days, you don't behave normally. No one behaves normally under high pressure circumstances. Gases are the same way. Okay, so which means that we need to account for that. So for that, there is this equation, okay, in which the gases are not behaving ideally. So this is the equation for real gases. Now, I don't need you to know this. I just want you to know that chemists do study gases or real gases. Okay, they do take account for that there might be some little differences between real gases and ideal gases. Okay, the other thing that is considered in real gases, which is not considered in ideal gases, is what is called intramolecular force. And what the intramolecular force does is the attraction and repulsion of gases. Remember, we said in kinetic molecular theory that there is no attraction or repulsion between gas molecules. But that doesn't happen under high pressure condition. High pressure conditions, all molecules are much closer together, so they can interact with each other. Okay, and those intramolecular forces then can be that of attractive or repulsive. And if they're attractive, you're reducing the volume. If they're repulsive, you are increasing the volume a little bit. So you have to account for that also. Okay, so that is how real gases and ideal gases differ, and it's pretty much in the volume and because of pressure. And this is it for gases. Okay, so gas stoichiometry is what we did. Now, all the other things that I talked about here with the molecular speed and all that, it's kind of nice to know, but I usually don't ask that in an exam. I don't give you any problems with that, so you're fine. Okie dokie.